This last section of the chapter introduces the idea of the electric field. The electric field is very important and the entire next chapter is dedicated to it. So in this video, I'm not going to cover everything about fields, but this is going to be the foundation of what we talk about here and the next chapter. Understanding fields can be a bit tricky since it's something that typically people haven't been exposed to before. So when we think about fields, it's important to understand this is a general idea. It's not only applicable to charges in the electric field. So the most common types of fields that you might be familiar with would be the gravitational field, the electric field, and the magnetic field. Now, the electric field is what we're going to study right now, and the magnetic field we will study in a few chapters. Now, you might pause when I say the gravitational field, because you know about gravity, you know about the force from gravity. And it isn't that the gravitational field is something special that you have to know general relativity for. But as we talk about fields, you might realize that it really does apply to the gravitational force as well. And we really use fields anytime we're talking about a long-range force, which was gravity. So to try to give you a starting point of what we mean when we talk about fields, here we're showing two bar magnets. Now this obviously is going to be the magnetic field, because these are magnets. And you've possibly seen a picture like this before, seen this as a demonstration somewhere in your education, that all of the lines are made up of little tiny bits of iron. And you see that it is tracing out these lines. So this tells you something about the direction. It doesn't show you very well the strength, but it does show you the direction. And you can see that this magnet is influencing the iron all around it. I mean, these two magnets together are filling the space with something, and we call that something the field. So before we talk specifically about the electric field, let's try to think in general about what fields are, what this actually means. So the first thing to know about a field is that it exists at all points in space. Now, when we say that it exists, the value could still actually be 0, and this could be at one or more points. But it still exists at every single point in space. So a field is never just constrained to be within a certain radius or within a certain box. There's going to be plenty of times where you have very large areas where the field might be equal to 0, but we say that the field exists at every single point in space. Now, the field existing, what we typically talk about is going to be the strength of the field at every point. And so obviously, there's going to be different types of fields, but if we're just talking about one field, such as the electric field, that's going to have a magnitude, right? So the magnitude is going to be a scalar quantity like 10 or 13.2. It's going to have units, and this is going to depend on the type of field that it is. Is it an electric field or magnetic field? Those have different units. And the last thing that our fields are going to have in general is going to be a direction. Once you see this idea of magnitude, units, and direction, you should think vector. So these fields are in fact vectors. Now the reason I put this in general is that every field we will talk about in this class is in fact a vector field. So when we talk about fields, they will always have a magnitude, unit, and direction. However, in physics, there are fields that are not actually vectors. So if you have a field that is in fact not a vector, well, then it doesn't have a direction. But all of our fields for this class will be vector fields with directions. So whenever we're using fields, we're trying to explain long-range forces. And long-range doesn't necessarily mean very far away. It just means not in contact. So obviously a push or a pull requires two objects to literally be touching one another, but we know that the gravitational force does not require the Earth to actually be in contact with a ball. So long-range forces just means not in contact. So when we talk about fields, they must be created by something. So one thing that's going to be a little bit tricky here is actually notation. Note that in this first part here, I'm saying charge Q, where this is capital Q, creates an electric field everywhere. And again, everywhere means every point in space. So we say that the field is created by charge Q. It's created by something. But then the field also interacts with other things or particles. It doesn't have to be a particle, it's just something. And for our electric field, that's going to be a different charge, lowercase q, which now has a force exerted on it by the electric field. Now, these 2 points are honestly the most important, and it's a bit tricky to understand. So one thing to note is that these 2 q's are not the same, right? Capital Q and lowercase q are not the same. Sometimes you're going to have Q1, Q2, Q prime. There's lots of different ways of distinguishing these. But one charge or one object is creating the field, a different one is experiencing it, or experiencing a force due to the field. So again, most of this is going to apply in general. These last 2 parts, for instance, you could imagine the Earth creates the gravitational field and a ball experiences the gravitational force due to the field. So these do still apply even if we're not talking about electric fields. So hopefully through some examples, this will make a little more sense. But these really are important things to understand about our fields. And fields are really going to be the foundation of a lot of what we talk about, so it's important to understand. So the book makes this distinction, and maybe this will drive home a little bit the point of why we're starting with this and why it seems so strange. In the Newtonian view, we just talk about forces. That's all. So this should look familiar. We talked about Newton's laws and forces between objects in the first half of intro. This is what we did. But with the Newtonian view, we just say that somehow A is exerting a force on B, and the fact that they're not in contact, well, we just worry about that. The book raises a couple of points of problems that we run into, and I'm not going to go into those here since those are very theoretical points. However, once we talk about long-range forces, in a Newtonian view, it doesn't really make sense. So the Faraday view is introducing this idea of a field, and this is what we're doing in this class. So A, object A, instead of directly acting on object B in the Newtonian view, A creates a field around it that fills all space. And so we can talk about how this field exists, what the value of the field is, what the direction is, etc. But the field is in space. Object B is somewhere in space and it then feels the field. That field then exerts a force on B. And you can think of the field in a way as being in contact with B because they're at the same location. So this is a little more confusing simply because it's new, but it is a nice way to think about long-range forces. So that's what we're doing now as a way to get around the fact that long-range forces don't always make a lot of sense. So in the next video, I'm going to try to make a analogy about fields to hopefully help you think through this in a different way, and then we'll do the specific example of the electric field.